Today, I would like to briefly talk about prosthetic leg, what they are, how they work, and why they matter. A prosthetic leg is an artificial device used to replace all or a part of a leg that has been lost either through injury, illness, or a congenital condition. The main goal of a prosthetic leg is to restore mobility and independence, allowing people to walk, return to work, and participate in daily activities that many of us might take for granted. Let's look at the key components. First, there's the socket and liner, which are custom fitted to the user's limb. This part is crucial because it provides comfort and help distribute body weight evenly. For those with above knee amputation, a knee joint is included. This joint can be mechanical or even computer controlled using advanced technology to create smoother and natural movement. At the bottom, the prosthetic foot provides support and stability, and it comes in different design depending whether the user wants to walk, run, or play sports. Modern prosthetic legs are made from lightweight, durable material like carbon fiber, titanium, or aluminum. Some advanced models use hydraulic, pneumatic, or computerized systems to adapt to different walking speed and terrains. Customization is another important aspect. Prosthetic leg can be tailored to match a person's lifestyle and preferences. Some people choose realistic cosmetic covers, while others prefer a more technical look or even decorate their prosthesis to express their personality. In summary, prosthetic legs are not just medical devices, they are life-changing tools that help people regain their function, confidence, and independence after limb loss.
For our article review, we choose a study by Smith et al. From 2014, which focuses on robotic testing of prosthetic legs. The main idea of the article is that using robotic systems help evaluate the dynamic performance of prosthetic prototypes more accurately than human gait trials. Through this method, they were able to measure important data like displacement, velocity, acceleration, torque, and force with higher precision and repeatability. This is very relevant to our report because it shows how dynamic analysis plays a key role in improving prosthetic leg design. By simulating realistic movements using robots, engineers can better understand how a prosthetic would perform under different walking conditions. Overall, the article supports the idea that robotic testing is a valuable tool in making prosthetics more responsive, stable, and closer to natural leg movement.
Hi, my name is Dayang Farzana, and now I will be explaining on the methodology used in this study. To investigate the kinetics and kinematics performance of leg prosthesis, we conducted a comprehensive literature review using scholarly databases such as PubMed, ScienceDirect, and Google Scholar. Our focus was on peer-reviewed journal articles, conference papers, and technical reports from the past 10 to 15 years. We use targeted keywords like prosthetic leg kinematics, biomechanics of prosthesis, and gait analysis in prosthetic users to gather studies with relevant quantitative data. Specifically, we prioritized research that reported joint angles, velocities, accelerations, ground reaction forces (GRFs), and joint torques, especially at the hip, knee, and ankle. From these sources, we extracted gait cycle parameters such as step length, stride time, and joint kinematics and kinetics across various walking conditions and prosthetic leg designs. This enabled us to identify patterns in how different technologies impact gait mechanics. We also examined the effects of key variables including walking speed, amputation level, material composition, limb alignment, and the type of prosthetic foot or knee system used. To evaluate performance, we considered motion symmetry with the intact limb, energy efficiency, gait smoothness, user comfort, and reduced compensatory movements. Ultimately, this approach allowed us to assess which prosthetic designs most closely replicate the natural human gait, providing valuable insights into optimal biomechanical performance.
I will highlight the significant advancement in modern leg prostheses that have greatly improved the replication of natural gait. First, microprocessor-controlled prosthetic knees have revolutionized joint movement. They achieve a flexion extension range of 10 to 60 degrees during the swing phase, closely mimicking natural knee motion. The ankle joint also provides effective dorsiflexion and plantarflexion, which support push-off and foot clearance, resulting in smoother and more symmetrical gait patterns compared to traditional mechanical knees. From a kinetic perspective, these prosthetic limbs manage ground reaction forces effectively, with peak forces around 1.1 times body weight during mid-stance. Variable stiffness prosthetic feet improve energy return during push-off, reducing the metabolic cost of walking and lessening the load on the intact limb. This promotes a more balanced and efficient gait. Control systems have also advanced. The continuously varying task control model improved joint angle prediction accuracy by 15% over traditional methods. Using tight angle sensors, the system detects gait phases robustly, minimizing timing errors during transition. Real-time sensor feedback allows the prosthetic joint to adapt dynamically, optimizing stability and energy efficiency. Material innovation like carbon fiber composites provide an ideal balance of lightweight durability and flexibility. Integrated sensor network continuously monitor terrain changes, enabling the prosthesis to adjust for stairs, ramps, or uneven ground. Clinically, these advancements translate into faster walking speeds on uneven terrain, reduced fall risk, and improved long-term joint health. Most users prefer microprocessor knees for their natural feel and reduced cognitive effort.
Good day everyone, I am Nur Andriana and I'll be presenting about the kinetics and kinematic performance of prosthetic leg and how they impact real-life functionality and design. Let's start by understanding what kinetics and kinematics are. Kinematics describe the motion of the body without considering forces, focusing on joint angles, velocity, and movement pattern. Meanwhile, kinetic deals with the forces causing that motion, such as torque, muscle forces, and ground reaction force. In prosthetic legs, joint angle, gait phases, and range of motion are the key kinematic factors. For example, studies show that even with only on-board sensors, prosthetic can estimate walking speed within 0.6 meter per second and incline within 0.52 degrees, showing impressive accuracy. On the kinetic side, we consider factors like joint torques, ground reaction forces, and load distribution. These are critical to improve balance, energy efficiency, and shock absorption. Proper design helps prevent discomfort and long-term joint degeneration, especially in transfemoral amputees who rely more on the hip. So overall, studying both kinematics and kinetics allow us to study prosthetics that move naturally and work efficiently under real-life conditions. Now, let's move on to what makes a prosthetic perform optimally in terms of kinematics. To mimic natural leg movement during walking, running, or even jumping, we need to carefully reproduce the range of motion and gait cycle of a biological leg. The gait cycle includes two main phases, stance and swing, and further break down into 8 sub-phases such as heel strike, mid-stance, and toes off. Smooth transition between these phases prevent jerky movement and improve comfort. Another factor is stride length, ensuring that the patient's step size and rhythm match that of a normal gait. Technological advancements like microprocessor controlled knees or MPKs have been introduced to support this. This use of sensor detect position and load and adjust the joint's resistance in real time. A key feature of MPK is stance phase control, which enhance stability especially on uneven terrain. But it doesn't stop at the joint. A well-fitting socket is also critical to prevent slipping and enhance coordination between the user's movement and the prosthetic response. And of course, comfort and personalization must always be prioritized to support long-term usage. Even with all this advancement, prosthetic legs still face several limitations. Firstly, they lack sensory feedback. Unlike a biological leg, prosthetic can't yet feel the ground, so users rely heavily on their vision to avoid tripping or stumbling. Secondly, long-term use often lead to muscle weakness because muscle around the prosthetic area are underused and it can lead to imbalance and fatigue. Thirdly, while prosthetic are tested in controlled lab setting, many struggle in real-life situations leading to discomfort or instability. But there is still hope for improvement. One promising solution is the restoration of sensory feedback. For example, bone-anchored prosthetic can transmit tactile sensation. Also, EMG-driven biofeedback systems are being developed to restore lost perception. On the control side, advanced algorithms using deep learning and sensor fusion are helping in prosthetic joints better predict gain, intent, and adjust in real time. And of course, consistent user feedback is crucial to continue refining the design to match patient real-life needs and comfort. So the goal remains the same: create prosthetics that are more natural, adaptive, and supportive, enabling users to move with confidence and comfort. That's all for me. Thank you. To conclude, designing a prosthetic leg goes beyond just using mechanical parts. It requires a solid understanding of human biomechanics, including joint angles, gait phases, ground reaction forces, and torque. These factors are essential to create movement that feels stable and natural. With recent technologies like microprocessor-controlled joints and sensors, prosthetic legs can now adapt to walking speed, terrain, and incline. Materials such as carbon fiber also help reduce weight while maintaining strength and comfort, especially for daily use. Even so, some limitations still exist. Most prosthetics do not provide sensory feedback, so users rely more on vision than body awareness. In real life, performance can differ from lab results, and issues like discomfort or muscle weakness may appear over time. Moving forward, the focus should be on improving personal comfort, real-world function, and long-term usability. By combining user feedback with new technologies, prosthetic legs can continue to evolve, not only to support walking, but also to help users more confidently and comfortably every day.